warahmatullahi wabarakatuh. In this video, we will be presenting about Semi Analytical Iterative Method for solving Michaelis Menten Kinetic Enzyme reaction, which is supervised by Dr. Mak Salim Selamat. My name is Nur Afifah binti Mama Ahe.
My name is Filzah binti Zamani.
My name is Luciana Usul-Robert. The Michaelis Menten equation is a nonlinear differential equation that is used to describe the rate of enzymatic reaction. In the previous study, several methods such as Adomian Decomposition Method (ADM), Variational Iteration Method (VIM), and Homotopy Perturbation Method (HPN) have been applied to solve Michaelis Menten equation. However, the result shows that this model have the complexity to converge the iterations. Hence, a new approach with faster convergence of iteration will be presented in this study. The method is called Semi Analytical Iterative Method, or SAIM. SAIM is introduced to solve Michaelis Menten equation, and Padé approximation were applied along with SAIM. The aqueous solution by SAIM-Padé are compared with ADM-Padé, ADM-Shanks, and Multistage Adomian Decomposition Method (MADM). In conclusion, the solution obtained by SAIM-Padé to solve the Michaelis Menten equations give a better convergence of solution.
Michaelis Menten Kinetic is first introduced by Leonard Michaelis and Mark Menten. The equation of Michaelis Menten refers to the rate equation of one substrate enzyme reaction. The increase of substrate concentration will lead to the increase of rate of enzymatic reaction. Michaelis Menten equation is in the form of nonlinear equation. Thus, numerical method is a practical method to solve this problem. It will deal with the initial value issues in ordinary differential equation. One of its alternatives is Semi Analytical Iterative Method, or for short SAIM. SAIM is a method proposed by Tamimi and Ansari that produces analytical approximation solution to linear and non-linear problems. It provides quick and realistic analytic of solution without the need for linear and discriminating. To handle the boundary condition at infinity, Padé approximation is one of the approach that be applied to the convergence series solution.
Previous study shows that the calculation of Michaelis Menten equation is difficult to solve and it could take large memory in the computer. Also, the convergence of the iteration method is difficult to achieve since it delicate to the initial condition and the number of unknown in the differential equation. There are three objectives of the project. The first one is to solve Michaelis Menten equation by using Semi Analytical Iterative Method (SAIM). The second objective is to determine the accuracy and efficiency of Michaelis Menten solution using SAIM to validate the result. And the third objective is to compare the result of SAIM with ADM-Padé, ADM-Shanks, and MADM.
The significance of the project is to get a better convergence of solution of Michaelis Menten equation, since the convergence of iteration method and the calculation is very difficult, while the benefit of the project is to provide a simple method that can converge the solution easily and to show that SAIM give a better approximation of Michaelis Menten equation. Lastly, the scope and limitation of this project will be solving Michaelis Menten equation using SAIM.
Michaelis Menten equation is a model used for enzymatic reaction. This model approximates the original dynamic by assuming the concentration of the enzyme remains constant. In this mechanism, a substrate A is reversibly bound to an enzyme E to form an enzyme substrate complex Y that react irreversibly to produce a product X and release the enzyme E. The system of the differential equation can be written corresponding to the dynamic of this reaction, which are shown in equation 2.2, 2.3, 2.4, and 2.5, with the initial condition shown in equation 2.6. The equation 2.2 until 2.5 can be reduced to two equations for A and Y, which can be seen in equation 2.7 and 2.8 with initial condition in equation 2.9.
Next is the previous method of solution for Michaelis Menten Kinetic Enzyme reaction. In 2019, Swaminathan, Narayanan, Mohan, Saranya, and Rajendran used Homotopy Perturbation Method to solve diffusion equation of Michaelis Menten kinetics in macrodisc biosensor. Raham and Tunisa and Rajendran 2008 used Variational Iterative Method to derive the approximate and analytical solutions of nonlinear reaction diffusion equations, which contains a nonlinear term related to Michaelis Menten Kinetic Enzyme reaction. Siva Sangari and Kartibol 2019 used Adomian Decomposition Method to solve the immobilized enzymatic kinetics with the Michaelis Menten mechanism for an irreversible reaction without external mass transfer resistance. Asok Kesen 1986 used Adomian Decomposition Method with Padé to solve the concentration of intermediate complex, which represented by the Michaelis Menten solution. Wahidi and Jalalvan 2012 used Adomian Decomposition Method with Shanks to contradict the divergence series in Michaelis Menten equation. Lastly is Hashim and Mak Salim Selamat 2008 used Multistage Adomian Decomposition Method to simulate the total time evolution of the reactant concentration in the basis enzyme substrate reaction.
Semi Analytical Iterative Method is a method proposed by Tamimi and Ansari in 2011 to solve nonlinear differential equation. It is an approach that incorporates various tools at problem solvers' disposal, which combine the analytical, symbolic, and numerical computation. These are the examples of the application of SAIM throughout the years. To further improve the convergence of iteration of the method used, Padé approximance is applied. Padé approximance is a method developed by Henry Padé in 1890, and the idea and the analyzation of the method is presented by George Frobenius. By using Padé approximation, there lies the possibilities of deducing from any converging and diverging series of powers. These are the formulation of Padé approximations according to Fowey, 2007.
The process of the research starts by set the value of alpha equals to 0.375, beta equals to 1, and epsilon equals to 0.01. And then apply the SAIM to Michaelis Menten equation using Maple. Then we find the iteration using Maple and we check the convergence of the iteration. If the iteration cannot be converged, we apply Padé approximation to achieve the convergence of SAIM. But if the iteration can be converged, then we compare the direct numerical method and Padé approximation with ADM-Padé, ADM-Shanks, and MADM.
The formulation of Semi Analytical Iterative Method, SAIM, is referred from Tamimi and Ansari, 2011. First, a differential equation is written as the equation above. Then, U0 x is assumed as an initial guess of the solution to problem Ux. To produce the next improved solution, the following problem is solved for the next iteration using this equation. Then, a simple iterative process is produced as an efficient solution of linear sets of problems. Each of Ux is a standalone solution to the problem, and each solution is an improvement of the previous iterate.
In this work, we consider these two equations, subject to initial condition x0 equal to 1 and y0 equal to 0. In view of SAIM, we have the following equations. Thus, the primary problem to solve are Lx0 t equal to 0 and Ly0 t equal to 0, with x0 0 equal to 1 and y0 0 equal to 0. The general iteration problem can be done through the following equations, with xn plus 1 0 equal to 1 and yn plus 1 0 equal to 0. We can get a solution that is convergent to the solution of equation by increasing the number of iterations. The iteration can be carried through using the given equations with initial value x0 t equal to 1 and y0 t equal to 0. The parameters for alpha is 0.375, beta is 1, and epsilon is 0.01. To solve this problem, we compute it using Maple. This is the solution for the first iteration, and this is the solution for the second iteration. As a result, the last iteration for x solution is iteration 12, while the last iteration for the y solution is iteration 11. The result is shown in the following figures.
Padé approximation is applied to the solution of SAIM to converge the solution. This table shows the results of SAIM with Padé for parameters x and y. The results is compared to the solution of Range-Kutta method. The first figure shows the comparison between the solution of x by using Range-Kutta method and by using 12 terms of SAIM-Padé. The second figure shows the comparison of y solution using Range-Kutta method and using 11th term of SAIM-Padé. It is observed that both results of parameters x and y matches the Range-Kutta method solution really well.
The table shows the y solution of SAIM-Padé, ADM-Padé, ADM-Shanks, MADM as compared to Range-Kutta 4. For your information, the result of ADM-Padé, ADM-Shanks, and MADM are taken from Hashim and Slamat article in 2008. The graph indicates the comparison of y solution of SAIM-Padé, ADM-Padé, ADM-Shanks, MADM with Range-Kutta 4 solution. From the graph, we can see that the solution of ADM-Padé and ADM-Shanks are not good enough to simulate the Michaelis Menten reaction, especially after t equals to 0.2. But the other two methods, which are MADM and SAIM-Padé, seems to have more accurate result as it is closer to the Range-Kutta 4 solution. By taking the 11th term of SAIM-Padé, it is clear that this algorithm matches the Range-Kutta 4 solution. The table shows the absolute error of y solution between SAIM-Padé, ADM-Padé, ADM-Shanks, and MADM with Range-Kutta 4. The graph shows the comparison of absolute error for y solution between SAIM-Padé, ADM-Padé, ADM-Shanks, MADM with Range-Kutta 4. From the graph, we can see that the absolute error for ADM-Padé and ADM-Shanks keeps on increasing when t increases. Meanwhile, the absolute error for MADM and SAIM-Padé are almost the same. However, the absolute error for SAIM-Padé starts to increase at t equals to 0.5, while for MADM is almost 0. It shows that MADM has better accuracy as compared to SAIM-Padé. However, MADM has longer calculation and it uses larger memory space to obtain the solution. If the calculation was taken into consideration, the application of SAIM-Padé gives better solution to solve Michaelis Menten equation.
In conclusion, we have successfully achieved the three objectives of this project. For the first objective, the convergence of iteration method of Michaelis Menten was successfully solved by using SAIM with the application of Padé approximations to execute better convergence. For the second objective, the value for both iteration of parameter x and parameter y matches with the Rasch-Kata method solution, and it shows that the solution of SAIM-Padé is accurate and efficient. For objective 3, the solution of SAIM-Padé and ADM is closest to Rasch-Kata method solution, and the absolute error is closest to 0. However, the use of SAIM-Padé is more efficient and time-saving, as the solution of ADM can be obtained by using longer calculation and could take large memory space and time-consuming. Hence, Semi Analytical Iterative Method with the application of Padé approximants is proved to be effective and efficient in solving Michaelis Menten Kinetic Enzyme equation.
The recommendations of this research is to apply SAIM with Shanks transformation as an acceleration strategy to solve Michaelis Menten. Next is to solve the Poisson equation from incompressible Navier-Stokes equations using SAIM. Lastly is to solve the Predecker-Pray model with SAIM.